Okay, so in this problem, we're going to learn how to do a method called Icebox. And first of all, when we are going to use Icebox is if we're given initial concentrations and asked to find either equilibrium concentrations or KEQ, and not given enough equilibrium concentrations to find KEQ. So how we're going to do Icebox is, so first the question is, initially 4 moles of A and 2 moles of B are placed into a 2-liter container. At equilibrium, there are 0.6 moles of C present. What is KEQ? So we're asked to find KEQ, and we're given some initial concentrations and a single equilibrium concentration. In order to find KEQ, typically we need all equilibrium concentrations for all of our reactants and all of our products, so that we can do our concentration of our reactants, our concentration of our products divided by our concentration of our reactants. But since we're not given all of the equilibrium concentrations that we need, we have to use Icebox. So first of all, the first thing that catches my attention is that I have 4 moles of A, 2 moles of B in a 2-liter container. In order to do Icebox, I need concentrations. So I need to find my concentrations for each of my A and my B. So my A concentration is going to be, I'm going to use molarity as my units of concentration. So molarity is moles over liters. So my A is going to be 4 divided by 2. So it's going to be 4 divided by 2 is 2 molar. My B, on the other hand, is going to be 2 over 2, which equals 1 molar. So now that I have my concentration values for A and B, and we can do C too, so it's going to be 0.6 divided by 2, which is going to be 0.3 molar. So now that I have my concentration values for A, B, and C, for all the values that I've been given, now I can form my ice table. So to form my Icebox or my ice table, first I draw lines in between all of my compounds. So wherever there's a plus or the arrow, we're going to draw lines. Then we're going to write I for our initial concentration, C for our change in concentration, and E for our equilibrium concentration. And then we're going to put lines in between them to complete the table. Now we're going to input all of the information that we've been given. So we know that our initial concentration of A is 2 molar. And our initial concentration of B is 1 molar. And we haven't been given the initial concentrations of C or D, so we can assume that there's 0. And then we've been given the equilibrium concentration of C. So that's going to go down here in the equilibrium column. So we put our initial concentrations in our initial row, and now we're going to put our equilibrium concentrations in our equilibrium row. So this is going to be 0.3. And that is all the information we've been given. So now we have to continue to fill in the table, but we haven't been given any other pieces. So our next step is we're going to fill in plus and minuses based on how our concentrations are going to change between initial and equilibrium. So for our A and our B, we're starting with concentrations of A and B, so that we know as we combine them to form our products, our concentrations are going to decrease. So we're going to put negatives for our reactants. In our products, we're not starting with anything in our products, so our concentration needs to increase. We can't create negative amounts. So in our products, because we're not starting with anything, we're starting with 0, we put pluses in our concentration change boxes. Now to help us figure out how to calculate our equilibrium concentrations, we're going to substitute our compounds for x's. So everywhere there's a compound, we're going to put an x. So over the A, the B, the C, and the D. If there's a coefficient, we're going to bring that coefficient along. And so what our equation says is that for every 1 mole of A, 2 moles of B, we are going to create 1 mole of C and 2 moles of D. So we can represent this using X's to help us use those ratios to figure out our equilibrium concentrations. So now I'm going to bring those X's and 2X's down into the change row. So that's going to be X, this is going to be 2X, X, and 2X. Now, since they gave us one equilibrium concentration, I can actually find a numerical value for the change in concentration for C using I plus C equals E. So I plus C equals E. So I know that I is 0 and E is 0.3. And then it's going to be a positive number in C. So 0 plus 0.3 is going to give us 0.3. Now I have a value for X. So everywhere there's an X, I can put in a 0.3. And if X is 0.3, 2X is 0.6. Now that I have my change row filled out, using I plus C equals E, I can easily fill in my equilibrium concentrations. So my equilibrium concentration for A is 2 minus 0.3, which is going to give me 1.7. 1 minus 0.6 is going to give me 0.4. I already have my equilibrium concentration for C, and my equilibrium concentration for D is going to be 0 plus 0.6, which is 0.6 as well. So now we're not quite done because it didn't just ask us for our equilibrium concentrations. It asked us for our KEQ. So I'm going to make this a little bit smaller so we can work over on the side. So my KEQ, I know that the equation for KEQ equals the concentration of my products over the concentration of my reactants. Remember, brackets are shorthand for concentration. So for this equation, it's going to be C times D squared. Wherever there's a coefficient when you're doing your KEQ equation, that coefficient becomes an exponent over our reactant. So concentration of A times the concentration of B squared. Now all I need to do is plug my information from my equilibrium row into this equation. Okay, because I'm finding my KEQ, so I need to work with my equilibrium concentration values. So KEQ equals C is equal to 0.3 times 0.6 squared for D times A is equal to 1.7 times 0.4 squared for B. And when I put this in my calculator, I get 0.397. And when you're doing this in your calculator, you want to put 0.3 times 0.6 squared divided by, in parentheses, 1.7 times 0.4 squared, close parentheses, to keep your order of operations correct so that you get the right answer. So your KEQ for this equation is 0.397, found using Icebox.